All right, for our last video, we're going to cover 5.4, which is finding empirical probabilities. And really, we did this during lecture when we were flipping the coin, and then when I was simulating flipping the coin in StatCrunch. So we're just going to revisit that with another example, and I'll give you some other options, other methods for flipping. So in the book, they're using a UCLA statistics applet bank, okay? But here, I mean, since we're using StatCrunch, I will show you how to do all of this in StatCrunch, okay? But really quick, as far as simulation, okay? If you want to simulate an experiment, just like how we simulated couples kissing the right way, the steps are just kind of like this: is one, identify the random action and the probability of a successful outcome. All right, so here, random action was, I mean, if you think about kissing the right way, it was tilting your head to the left or tilting your head to the right. And as far as a successful outcome, is just, I mean, it just means what outcome are you counting, the successful or the failure, the heads or the tails, right? So here, I guess in this case, it would be tilting your head to the right. And then here we want to determine how to simulate this random action. So do you want to flip a coin, which is fine, right? Or do you want to use computer software to help you do it, or StatCrunch? 3, determine the event that you're interested in. So of course here, maybe we're interested in the number of heads out of 20 coin flips, which in this case was the number of times they tilted their head to the right out of the 20 couples. So that means we have to add them up after we flip everything. And then explain how you simulate one trial. So I mean, in class we flipped a coin, that was one way. And also we could be using StatCrunch simulate simulator for us. Okay, how that works is a little bit more code involved, but you could just say use StatCrunch. 5, we carry out a trial and record whether or not the event of interest occurred. So pretty much after the 20 coin flips, we recorded the number, right? And then what did we ask? Well, we asked what's the probability that 8 out of the 20, right? 8 out of the 20. So we're counting the number of 8s that occur out of the total number. Okay, but here it's saying repeat the trial many times, at least 100. Actually, it should be at least 1,000 given the computer, but it says count the number of times the event occurred, right? So what we did with our dot plot? Remember, we had a dot plot that looked really nice. We just counted the number of dots where we observed 10, and then we put that 10 over the total number of dots that we had, right? Number of times that we simulated the experiment. Okay, and 7 is the number of times the event occurred divided by the number of trials is your voila empirical probability. Okay, one thing to briefly note here is that the summary of steps for simulation. So when it says at least 100, where are they getting this number from? And so there's theory backing up everything that we're doing when we flip a coin or when we're with the computer. But it's saying that the law of large numbers states that if an experiment with a random outcome is repeated a large number of times, the empirical probability of an event is likely to be close to the true probability. Okay, so the larger the number of repetitions, the closer these probabilities are likely to be. Okay, so the thing is that these true, they're really talking about the theoretical probability. I mean, sometimes those can be tough to do using theory because you need math, and as we all know, math can be difficult. So what would be easier if I know how to simulate the coin flip? I could just do that a whole bunch of times using technology, and my number, the empirical probability, is going to be just as good as the true probability for the sake of making decisions. Okay, so let's see another example. So last time we did kissing the right way. This time we'll do rock paper scissors. Okay, so in this example we won't be able to flip a coin, and you'll see why. But rock paper scissors game, it works like this. Okay, you go 1, 2, rock, paper, scissors, shoot. And you play with 2 people and you go rock, paper, scissors, shoot. And we all know that rock beats scissors, paper beats rock, scissors beat paper. Okay, so this game here is considered to be, right? Shushaling is the first name they found on paper, coming back from the, I think, 1600s or even earlier in Asia. But it says, have you ever played rock, paper, scissors, or Rochambeau? It's considered a fair game and that 2 players are equally likely to win, like a coin toss. Both players simultaneously display 1 to 3 hand gestures, rock, paper, and scissors, and the objective is to display a gesture that defeats that of your opponent. Okay, if you're really interested in rock, paper, scissors, you can visit the World Rock, Paper, Scissors Society at worldrps.com. Okay, but the main jest is rock beats scissors, scissors cut paper, and paper covers rock. Sen Sukumiken, okay, another name. But we ask, is it really a fair game? Okay, is it really a fair game? Okay, so these people, they're called game theorists, and they're all about what's the best strategy for playing games. So in here it says, do some players exhibit patterns in their behavior that an opponent can exploit? So in this article published in College Mathematics Journal in 2009, they found that players, particularly novices, tend to not prefer scissors, right? So if you're playing someone who's not familiar or hasn't played the game too much, they're less likely to pick scissors. So that means you should be more likely to pick, well, they're less likely to pick scissors than you could pick paper a little more often, maybe, right? So anyways, so we read this paper and we say, oh, novices tend to not prefer scissors. So let's see. So we say, suppose you decide to investigate this tendency with a friend of yours who hasn't played the game before. Okay, you explain the rules of the game and play, sorry, that's not 50, that's 40 rounds. Okay, so, you and your friend are there just playing the game. Rock, paper, scissors, rock, paper. So suppose your friend chose only 8 scissors 8 times in those 40 plays. Okay, so definitely it's a small number, right? Definitely less than a third. Okay, so what we want to do is say, well, how likely is it that we observe that given that there's no preference? All right, so what we want to do here is see how likely is it that we observe this outcome, right, given that there's no preference. Okay, so and in terms of no preference here, we're saying, well, no preference means no preference here means that each outcome is equally likely, rock, paper, scissors. So therefore, probability scissors here is 1/3. Okay, so here we can't flip a coin, right? Because we all assume coins are 50-50. So unless you have a coin that's a 1/3, it's 2/3, we could do it. But here, obviously, we can't use the coin. So we really need the technology. I mean, another way around is you can roll a die, like 1 and 2 could be scissors, and 3, 4, 5, 6 can be not scissors. But I mean, anyways, so really what it's asking you to do is saying, what's the probability that we get 8 scissors out of 40 plays, given that the probability of scissors is 1/3? Okay, so it's kind of like similar to flipping a coin 3 times and getting 3 heads, that type of problem. But the issue here is that it's probability of just getting 8 scissors out of the 40, right? So this 8 scissors, I mean, where can it occur, right? Is it the first 8 plays, or the last 8 plays, or the middle 8, or how many different ways can 8 scissors show out of the 40 plays, right? If we have game 1, game 2, game 3, game 4, game 5, game 6, right? In which of those 40 games or 40 plays do the 8 scissors show? So really, we have to count each of those outcomes and then use our independent multiplicative rule to find the probability. But you see, theoretically, or the real probability, I mean, that just sounds like a lot. Okay, so what I'm going to do here is try to estimate this probability using empirical, okay, which works like this. So what I'm saying is can we flip a coin like we did yesterday? No. So now we're going to use StatCrunch to help us out. So the StatCrunch has this coin built into it where it's 1/3 heads and 2/3 not heads. Okay, so here our outcomes for each game, it's either scissors or not scissors. Okay, because we're just interested how many times our friend selects scissors. So scissors or not scissors, scissors or not scissors. Right. So in not scissors, right, that's paper and rock. Right. So these two events are mutually exclusive and complementary. So let's see what this will look like in StatCrunch. And so I'm going to go into StatCrunch and I'm going to plug into these fields here. Okay, but I'm going to do what I did exactly last time in class. So the rows here is 40. So that's going to be the 40 games played. Okay, the 40 games played. And then what I'm going to do for columns, I'm going to put 100. So that's 100 trials or 100 experiments. So pretty much what I'm doing is I'm going to simulate 40 games being played 100 times. Okay, so I have 100 of these results from 40 games. Okay, so for each of the 40 games, right, we're going to flip a coin, right? From game 1 to game 40, we're going to flip a coin. And the probability of scissors is 0.3. Okay, so what I'm gonna get is just a bunch of zeros and ones in StatCrunch. 0 if it's not scissors, 1 if it's scissors. Okay, so after the 40 games are played, I want to count the number of times we got scissors. So that's what this is doing here. So for each column or sample, right? So in this case, our sample is the sample of 40 that we played. I want to sum the Bernoulli. Okay, and I'll go ahead and show you how to do that. And so that's going to count the number of scissors out of 40 plays, right? And then here I'm going to open a new table. So let me show you how I do that here. Okay. Okay, so if you go to StatCrunch here, you could just click on Open StatCrunch, and that would just give you a fresh blank sheet here. Okay, and then from here, we go to Data, and then from Data, we go to Simulate. And so here are the different options for simulating. Okay, so this Bernoulli is like the coin flipping thing. Okay, so we click on Bernoulli here. Okay, so the rows, I want to be 40. The columns, I want to be 100. The probability of heads, I want to be 0.3. And then here, I want to compute, I want to sum each column. So I write sum, and I want to this column. So there's only one column here, so we click that one there. And make sure to double click it so that it appears there. Okay, we close the parentheses. Make sure you can close that parentheses there. Okay, and then we want to click OK. Right, and so what I do here is, so this dynamic seed is just part of the random generator, but anyways, we could just go here to compute. Okay, so we compute here, and that's what we get here. So this whole row here, see, you get 100. So this is 14 represents 14 scissors selected out of 40 plays for this experiment. 13 out of 13 scissors selected out of 40 plays. 10 scissors, 11, 14, 16, so on and so forth. Right. So if we really want to get a good visual, so we get all the way to 100 here. So let's get a good visual here. So let's graph. Let's look at, we could do dot plot again, and then we could do of sum Bernoulli. That's the only column we have. And if you want, you could look at the mean and the median, and then we can compute. Okay, and this is the result that we get here. Okay. Okay. So if you see here, we get all of, I mean, kind of looks bimodal here, but we do get some randomness there. That's why we use more than 100, right? So the book says at least 100. It should be really at least 1,000. All right, but anyways, if we just use that 100 there, okay, these are our results. And actually, you can't see the median because it's pretty much right behind the mean, okay? Because it's this distribution, if you simulate it more, it'd be pretty symmetric. But we see the outcomes, right? So we see 12 scissors selected. This is like the number times 12. So let's go to 8 in this case. Okay, that's 11, 10, 9, 8. Right? So I want to know how many times did 8 appear. Right? So if I just highlight it, right? And if you go down here, it's 7. Right? So what I get here is 7 of of the 100 games we simulated, we saw 8 scissors selected out of 40 plays, right? And if you look here, as far as common values, like nothing went past 21, right? And then here, nothing went below 5. Okay, so what this does, it kind of gives you a range of values that we should expect to see if there's no preference in what they select, right? So this is kind of what this represents, are like the typical values of the number of scissors we should expect to see if there's no preference. And if you did 1/3 times 40, you would get roughly around 13 here, and that's where this is centered, or right a little bit less than that, but right around 13. Okay, so let's get back to the probability. So what's the probability? So I know that 8 times I saw 8 scissors occur out of the 100. So therefore, so this is what I did here. Okay, and I just want to note here that here was a separate simulation. Okay, it's a separate simulation of 100 again. And you see the graph doesn't look exactly the same, and it shouldn't, right? Because each outcome, each game of 40, it's a random outcome, right? But we do more or less get they're not completely different, right? The largest value was 20 here, the smallest was 5 here. We kind of get the same looking distribution here, right? So for this particular, I got 6, right? I got 6 here. So there were 6 times, 6 rows, 6 times, 8 scissors was selected out of the 40. Therefore, my empirical probability of observing 8 scissors out of 40 plays, given that the probability of scissors is 1/3, is 6 over 100, or roughly 6% chance. Okay, so what it's saying, hey, there's a 6% chance of observing your friend observing 8 of the 40 scissors, given that given that there's no preference. Okay, so I mean, it's kind of a small chance of happening, right? But that's how we find that there. Okay, so just to go back to StatCrunch really quick. So really, these as far as this data here goes, if I were to go and edit here, right, this columns is really small. Okay, it should be 1,000. Look, I could even put 10,000 there, right? So what it's gonna do is it's gonna flip this coin 40 times, count the number of heads or the number of scissors, and do that process 10,000 times. Okay, that's really what we should have there, because there's no reason to stop at 100 given that we have technology. Okay, so this number should be much larger. But anyway, so that's what we get here. Okay, so I'm gonna open it in a new table and I'm gonna compute here. Okay, so look, it takes a little time, but look here. So now I have the outcomes, but look, it goes all the way down, not to 100, but to 10,000. Okay, 10,000 there, right? So here I could do the same thing. I could graph and do a dot plot. I could do a dot plot of this. I could look at the mean and the median, and I could compute here. Okay, and look at that right there. Okay, that looks like the good old Christmas tree that we saw earlier, right? And then here I could go and highlight where 8 was. Okay, I think that's 6, 7, 8. I think this is 8 right here. I believe it was 8. And see, it gives us here 590 rows. Okay, 590 rows, right? So if I were to do 590 divided by 10,000, I would get 5.9%. Okay, I would get 5.9%. So you see here, I mean, really, we don't get anything that's much different from the 100, right? And from doing 10,000, I got 5.9%. From doing 100, I got roughly 6%, right? So doing 100, I mean, there's no reason why we shouldn't do more, but it's still okay in finding the probabilities here. Okay, so anyways, actually what we're doing here is a binomial distribution. So binomial distribution it's all about counting the number of coin flips out of n coin tosses. So in your book, they kind of talk, they have you go to this binomial calculator without explaining it. And really, the coin flipping example makes more sense, but binomial, it's already built in that it's going to flip this amount of coins. So, and then count the number of heads. Okay, so binomial is just a bunch of coin flips added up. That's all it does. Okay, so you could also use this function binomial. So we're saying we're going to do this binomial experiment 100 times, and here we're only going to do one column. Okay, but here we're saying for the binomial, we're going to flip a coin 40 times, and the probability of heads is 30%, right? Or for our example, we're going to play the game 40 times with the probability of scissors 30%, right? And each time we run this, we're going to count the number of times scissors was selected out of the 40. Okay, so the what I don't need to do here is add this function here. Okay, so that's one convenience of using the binomial simulator, because I don't have to add this function in here. It's already going to do it. Okay, so if I did that, then I would go into here, and then I would histogram this, and I get roughly a similar result. Okay, here it gave me 5. There's always a little bit of variation. Okay, a little bit of variation, but you see I got 5, then I got 6 in the other one, and then when I simulated, I got 559, right? So they're all very close to like 5-6%. Okay, they're all very close. That's why these are empirical probabilities, right? We're trying to estimate the true probability, and you see they're all close to around 5-6%. But just to show you real quickly how I do it in here. So if I do data, and then I go simulate, and then I go to binomial. Okay, so here we're saying the rows is 100. We only need one column, and here this is going to be, well, I'm going to flip the coin 40 times. I'm going to play the game 40 times, and the probability of scissors is 0.3. And so binomial already is going to add up all the scissors, all the number of times scissors. So that's why we don't need to click on this again. And then I could just open this data in the new table and compute. And then from there we can do our graph and do a dot plot of our results here. And then we get this example here, right? So I get this here. So this is always variation at different samples. Okay, so here this is 9, 8. Oh, that's 8 there. Okay, so if I highlight there, what do we get? Oh, we get 5. Okay, so I did it 100 times. I simulated this game, these 40 plays 100 times, and what we found is that 5 out of the 100. So we get 5% again. Okay, 5% again. All right, so so that's what I did here. Okay, but I just want to show you that extra example, because in the textbook they're having you go to the UCLA website, which is, it's a great website. They do they have little applets there for stats, but for us, we're gonna stick to using StatCrunch because it does it, and it does it better because it has these things built in where you can easily find the number with ease. Okay. Anyways. Say you want to do something different, okay? Say you want to simulate like rolling a die, right? And so what I'm saying is pretty much this Bernoulli, right? Flipping a coin, you only have 2 outcomes that you can record, right? Only 2 outcomes. And even kind of with the binomial, you're just summing all these heads, right? See, the heads or tails. But what if you want to simulate something that has more than 2 outcomes? Right, like you're rolling a die, right? Obviously that has 6 outcomes. How do you do something like that? Well, the Bernoulli or the binomial, they're not going to help us out there. So what we do is simulate uniform. Okay, so uniform implies that each outcome is equally likely. So it's a fair die built in already, right? So here I could simulate 100 rolls. And here I have my maximum number of 1, my minimum number of 1, my maximum number of 6, right? And then here I'm just saying no rounding, so that way it just gives me whole numbers, right? Because if I do not round, it's going to give me like a bunch of decimal answers as well, okay? Which is very useful in other cases, right? But I can even change this from like 1 to 52, and now we're talking about pulling out 52 cards from a deck, right? Or I could do 1 to 38, right? The outcomes of roulette wheel. So there's a lot of different things we could do here. But for rolling a die, I'll just do 1 to 6, and then I can roll that up. And you know, a die what would you assume that the histogram of outcomes should look like, right? Because here a die, each outcome is equally likely. So if I were to roll the die 100 times, hopefully I see more or less an even number of 1, 2, 3, 4, 5s, and 6s, right? And so let's see how that looks in StatCrunch here. Let me just simulate that in StatCrunch. So here I'm going to go to data, and then I'm going to simulate again, and then I'm going to go down here to uniform. So I click on uniform here, and then here I want, let's do it 100 times, and I just one column, and my maximum number is going to be 1. I'm sorry, my minimum number is going to be 1. My maximum number is going to be 6. Right? If we wanted to compute some stuff here, we could, but we're not. We're just recording the outcomes of the die. Okay, and then from here, I just want it to round to the 0 decimal place. So what that guarantees here, that I get whole numbers. Okay, 1, 2, 3, 4, 5, or 6. Okay, so I'll compute. Okay, and I forgot to hit an option here. Let me hit another option. Okay, I wanted to open in a new data table. Boom, there it is. So this is, I roll a die, get a 3. Roll a die, get a 5. Roll a die, get a 6. Roll a die, get a 3, 4. And you see here I have 100 of them. Right, 100 of them. All right, so if I were to graph this histogram, what do you think it would look like? Do you think it would look, you know, like the other ones? Unimodal symmetric, right? Or would it look like something else? Right? Let's see. Let's see. I mean, each outcome is equally likely to occur, so hopefully we should see the same number, more or less. So let's see. Oh, here we go. Ooh, I don't know. 1 sure was the least frequent. 18, 22, 17, 20, 16. So these are all more or less around the same number, but 1 definitely didn't show up as much, right? It showed up 7 times. Okay, so that's why, you know, hey, you know what? Let's go back in here. Okay, let's go back in here. Let me do this here. Let me do data. Let me simulate again. Let me go to uniform. Okay, let me do 10,000 rows. Okay, in 1 column. Okay, and I'll do 1 minimum 6. Okay, and I want it to round to the 0 decimal place. Let's open this in a new data table. Go. So what this is going to do is going to simulate rolling a die 10,000 times. Okay, and record the outcome. So boom, there it is. So if you look at this here, this goes all the way down. So I'm looking at these numbers here, right? This is the number of the row. Okay, so we're 9,630. It goes all the way down to about 10,000. Boom. Okay, so now here what I'll do is I'll graph. Okay, and let's look at our histogram. Uniform. Let's look at it now. Ooh, you see here? So kind of looking a little more uniform, but not as much. Okay, not as much. Okay, so what do we get here? Are these the results here? And actually I know why. I know why this is doing it, and so we have to add some little tweaks here. But see, these numbers came out pretty much the same, but these didn't, and part of it came from this rounding error. But if I wanted to be a real stickler about it, I can go in here and do this. Okay, I can go in here and say, okay, this is a uniform. Let's do 10,000 again. Let's do 1. And then what I could do here is put like 0.51, and then here I could put 6.49. Okay, and then I can round to the 0 decimal place. Okay, and if I compute this, okay, I get that. And then what I'll do here now is I'll graph histogram the second one here, and boom, there it is. Okay, so that's how we do it. So it took a little tweaking to do, and the reason that I did that is because so now we see each outcome equally likely. At 1 and 6 were being shortchanged all the time, and the reason because when it generates a number, it's like decimal numbers. So originally it's like 1.1, 1.12, 1.3, 1.22, 2.11, 3. So all these things. So, and then it would round to the nearest numbers. So numbers between 1.5 and 2.5, they were getting rounded to 2, right? From 2.5 to 3.5, they would be rounded to 3. But for 1, only 1 to 1.5 were being rounded to 1, right? So it had half the amount of numbers in which it could round to 1. The same thing with 6, only 5.5 to 6 were being rounded to 6, right? So what I did is I added that 6.49 and I added that 0.51, so that way it would generate numbers that are in here and round to 1, and generate numbers that are up here and round to 6, right? So how I did that was just, using my math prereq, I guess, right? Just understanding how rounding works, and just noting that 1 and 6 were being shortchanged because they were missing half of the numbers in which they round to 6. Okay, but other than that, so this is just an example here. So other than that, I mean, as far as 5.4, it's empirical probabilities, and it's kind of just, you got to think of ways on how to simulate, and doing these, especially something like this, when we're dealing with the Bernoulli and flipping coins and finding, I mean, it's much easier to do using the computer than theoretically. Okay, and these empirical probabilities are much easier to do than the theory, unless you want to get into the math part of it. Okay, but that concludes our discussion on chapter 5, and when we come back to class on Tuesday, we're going to be in chapter 6. All right.